So let's do that. Why is that a constant? Notice that you don't know much about the motion, right? You don't know what the ellipse is, probably. You don't know how quickly the planet moves. You don't know much about the mass of planet and the sun and the interaction between them. But let's do some necessary mathematics. Let's do what we can. How do you check that something is a constant in calculus? Derivative is 0. So let's look at the derivative. Is that derivative 0? Do you know how to differentiate? Yes? No?
Yes.
Yes. So how do we differentiate? How do you differentiate this area on two vectors? Don't we use a product rule? Don't we know now that the area satisfies distributivity law? And didn't we see that whatever it satisfies distributivity law satisfies the product rule? So we can apply the product rule. The derivative is then, so why don't you tell me what it should be? Area of what? How do you apply the product rule? Area of r prime of t and v of t plus, is it plus? Plus what?
R of t.
R of t, yes. V prime of t. Okay, so let me put question mark here, because at this point I don't know if it is 0 or not. That's what I want to know, and I will just compute this derivative. So now, do you know what r prime of t is? Well, r is position. What's the derivative of position? It's velocity, isn't it? So derivative of r is velocity, exactly that velocity used on the second place. So the first term is actually area of v of t and v of t. Doesn't it make us happy? Plus the second term is r of t on the first place, and what's v prime? What's the derivative of acceleration? Exactly. And then we are happy to recognize the first term. It's 0. And that's what we expected, right? We expect everything to be 0. What about the second term? Why is that 0? Let me leave it in the form it is now. Well, you see, there is nothing I used about planetary motion to conclude that the first term is 0. Right? Well, it would be very strange, if I concluded the second term is 0 without using any knowledge of what we are talking about. It would be very strange to know that for any motion that number is constant. Well, it would not be a law discovered by someone, right? It would not be a great discovery. So we need to know something about position and acceleration to conclude that this is 0. So what do we expect? What would make this 0? Well, there's no velocity here.
Acceleration is constant.
Acceleration is constant.
Acceleration is 0, 0.
Well, acceleration is 0. Is acceleration of a planet 0?
No.
No. Unfortunately, no. Never. Well, what would make area of a parallelogram 0? Geometrically.
If R and A are parallel, or
If these two vectors are parallel. right? That's exactly what makes the area of parallelogram 0. So what we have to check is whether these two vectors are parallel, right? According to our expectation that it should be 0. So the question is, are these two vectors parallel? Well, we can see the position vector. Where is the acceleration vector?
Opposite direction.
Opposite direction.
It is in the opposite direction, because what makes planet accelerate?
Gravity.
Gravity, the sun, right? How does it make planet accelerate?
It's attractive.
Directly toward the sun. So this is where acceleration is. And of course, this direction toward the sun is the opposite direction to the direction from sun to the planet. So these two vectors have opposite directions. And therefore the area is 0. So as I said, this first step is as simple as this one. As soon as you know how to interpret or how to write down the integral, it will be like 5 lines simple computation and showing that area is indeed that integral. So the whole Kepler's law now boils down to 2 simple steps, and this is one of them. And well, it is great thing on its own. We applied only one idea to explain Kepler's law, right? The idea of area being a product. That's all new that we needed here.